All right, good afternoon, gentlemen. Today we are going to go over balancing and identifying chemical reactions. Now, this EdPuzzle is going to introduce it, but I will kind of go over it more in class and we will practice this concept. However, after completing this EdPuzzle, make sure you submit your notes as well as try the worksheet that is on Canvas that goes with this EdPuzzle. The first thing we're going to get into is just the basics of a chemical equation. The basics that you have is you have what are called the reactants, and the reactants is always your starting material. For you guys, it'll always be written on the left side, similar to how we have it here. So the reactants are what are reacting together to form your products. Your products are what you produce, and in this case, they're always going to be on the right side. Instead of using equal signs, we use these arrows, and they kind of show when a chemical reaction is happening. So, for example, in this case, I'm reacting H2 with O2 to produce water or H2O. When you are looking at each chemical equation, there are multiple parts outside of just the elements that are listed. The ones that I want to highlight here are the coefficients and the subscripts. The coefficients, which are in my red circles here, are always going to be a large number that is put in front of your elements, and these ones are always going to simplify the amount of molecules total that you have. So for example, I have two H2 molecules, I have one O2 molecules, and this produces two H2O. Now, the subscript, which is the little tiny number that is in my blue circles, are the number of atoms in the molecule. So for example, in each individual H2 molecule, I have two H's, and you can see that because they're two separately. In each individual O2 molecule, right, I have two O2s, and in each individual H2O molecule, I have one O and I have two H's. So again, those are going to be focusing on the atoms in the molecule, whereas coefficients are going to focus on the number of molecules total. So how many duplicates I have. The reason we have subscripts and coefficients is based on the law of mass of conservation. So based on the law of mass conservation, it states that matter is neither created nor destroyed during a chemical reaction. Essentially, what I'm saying is that the total number of atoms does not change. So the number of atoms of what I start with, or my reactants, is equal to the number of atoms I end with, or the products. The total mass on the front should equal the end. So if I start with 10 grams, I should end with 10 grams. So looking at like a sample of this is I could ask you questions similar to the one you have here, where I have calcium and zinc carbonate and I have the grams, and I'm going to produce calcium carbonate and zinc. Now, I do not know what my zinc is equal to, but because of the law of conservation of mass, I can solve that. To do that, I'm going to add what my start is, and I'm pretty much solving for x like an algebra problem. So on the reactant start, I'm starting with 64 grams and 192, so I'm going to add those together to figure out what my total is. When I do that, I know I'm starting with 256 grams. In this case, I pretty much have 152 plus my unknown. It's kind of like solving for x. So when I set those equal to each other, I know to find x, I need to take my 256 minus my 152, and that tells me, hey, I should have 104 grams of zinc on this side to follow that. You should never break the law of mass of conservation because you cannot create matter. If some of the matter disappears, it doesn't mean that it's destroyed. It could just mean like, hey, a gas formed and has escaped. Or maybe you spilled something. But no matter what, in a reaction, you should theoretically always have the same amount you start and end with. But remember to kind of take into consideration other outside factors that might vary that number. So now that we've gone over the law of mass conservation, looking at this picture where I have H2 plus N2 to produce NH3, what is wrong with it? If you said, hey, I do not start and end with the same amount of H's and N's, you are correct. This is where balancing chemical equations becomes important. So, I'll just move this up now. To do this, what I recommend, because we know we should have the same start and end, is I like to make a T-chart. In that T-chart, I like to have my reactants and my products. What I will do is I will start with my elements. So in this case, I'm going to do an N and an H, okay? And I'm just going to write what I begin with. So right away, I have two N's on my left side, and I have one N on my right side. Well, right away, I know that's not balanced. So now it's just kind of a simple calculation. I want to find my least common multiple. In this case, 1 can go into 2 times. So to get my number, my N's now at 2, I put a coefficient of 2 that is distributed to my N. So I have 1 times 2 to give me my total N's of my product side on 2. Now my reactants and my products match together, so I can move on to my H's. Now I look at my H's on the reactant side or the left side, and I have 2. But now, because I have this coefficient here, that is going to be distributed to my H, which has 3. I multiply 2 times 3 to give me a total of 6. So right now, that is not balanced. The least common multiple between these two is going to be 6. So I'm going to go on the left side, and on my coefficient for my H2, I will put a 3. 3 times 2 gives me 6. And now I am fully balanced. So then to simplify this down, here is what it would look like. So let's try another one together, and then you will try a few on your own. So same process as before, we're going to make our table. So I'm just going to simplify reactants and products to R and P. Okay, I'm going to start with Na, Cl, and F. So starting with my Na, on the reactant side, I have 1, and on the product side, I have 1. So perfect, that means I am currently balanced. Next, I go to my Cls. I start with my reactant side where I have 1, but I have 2 on the product side. So again, we're going to do our least common multiple. In this case, 1 can go into 2 times. I put a coefficient of 2 in front of my NaCl. That makes my Cl 2, and that is balanced. However, when I do that, that now changes the amount of Na that I had previously. So now I'm sitting at 2 NAs. So I need to go back to my Na and rebalance that. Again, least common multiple between 2 and 1 is going to be 2. I put a 2 on my product side. I now have a 2, and I am balanced yet again. My Cls remain balanced, and my NAs are now balanced, so I can move on to my Fs. On my reactant side, I have 2, and on my product side, because I have that coefficient, I have 2 total H's, so I am balanced. Anytime you see a blank space like this above, you can write in 1s, but it is always implied that there are 1s there. But again, you can write them if you so desire. Why don't you try this one on your own? Answer the multiple choice question that is on the EdPuzzle, and then once you're ready, we'll move on. All right, so now that you've tried this, let's go through it together. Again, I'm going to make my T-chart, my R and my P. Okay. I'm going to write nickel, and then I'm going to write my O. Okay. So starting off with my nickel, on the reactant side, I have 2. On my product side, I only have 1. That is not balanced, so again, I'll find my least common multiple. In this case, it's going to be 2, and I'm going to apply that on my product side. When I do that, I now have 2, and I am balanced. Next, I have my O. I have O with a 3 on the reactant side, and on the product side is a 2. Now, this one is a little bit different than before because I'm not multiplying by 1. In this case, 2 cannot go into 3, 3 cannot go into 2, but they can both go into 6. So 3 times 2 on that side will get me to 6. And 2 times 3 will get me to 6. And I am now balanced. Now, looking over that, when I added that 2 onto my Ni2O3, that did change my nickel on the reactant side to 4. So to fix this, all I need to do is take away that 2. Oh, come on. Oh, goodness. Okay. Take away that 2, and I'm going to change this number to 4. Now, when I do that, I suddenly have 4 on that side. I did not change the number for anything else, so I am fully balanced. Try this one on your own, and then I'll go over it with you in just a moment. All right, same process as before. We're going to start off with our reactants and our products. Now, what I recommend for these kinds of problems is you always want to save your H's and your O's for the end, mainly because you're going to be dealing with there we go, like where you have like an O in 2 positions. So being able to look at those separately should be helpful to you because you're going to have them in those 2 positions. So we're going to start off with our carbon. So looking on the reactant side, I only have 1 carbon, and on the product side, I have 1. So as of right now, those ones are balanced, so then I can move on and look at my H's. Now, looking at the H on the reactant side, I have 4 H's, whereas on the product side, I have 2. I'm going to look at my least common multiple, which in this case will be 4, so I'm going to add a 2 here to give me 4 O's. That is, or 4 H's, excuse me. Now I am balanced. Now the last one is I'm going to look at the O's. On the reactant side, I have 2, but on the product side, I have 2 plus, right, 2. That gives me a total of 4. So again, I'm going to look at my least common multiple. In this case, it is going to be 4. I put a 2 here, and that is balanced. These problems can be a little bit more complicated, and you will see them with more complications when you get into chemistry next year, but kind of keeping, if you see an element in more than one spot, separate and doing that at the end does help it be a little bit more successful. Now, when you're dealing with polyatomics, you want to look at them as if they're acting as one atom. So in this case, like my NO2, those ones are going to be like in parentheses. And so I'm just going to act them as one because otherwise you can have very minimal errors take place when you're looking at that. I want you to try this one on your own. We are going to go through it in just a moment, but I want to see if you can kind of figure it out based on what we've done previously. All right, I make my T-chart, and I'm going to save the polyatomics for the end just because it helps to make sure that things are not changing too much. So if I'm starting with my magnesium, on the reactant side, I have 1 because that 2 outside of my NO32 is only going to be applied to the polyatomic, and I have 1 on the product side. As of now, my magnesiums are balanced. Looking at my potassium, I have 1 on the reactant side, and I have 1 on the product. Same thing. And just like that, because I have 1 on each side, my potassiums are balanced. Now we need to look at the NO3s. On the reactant side, because I have the 2 is applied to the whole thing. So I have 2 here, whereas on the product side, I only have 1. So I'm going to identify my least common multiple, which in this case is 2, and I'm going to put a 2 in the front. That changes it to balance it. But when I do that, that does change my K on the reactant side to be 2. So I need to do the same on, or the product side, excuse me, to the reactant side. Now it is completely balanced. Now, balancing chemical equations comes into play when you're focusing on the types of chemical reactions. There are 5 that we really need to know, which is synthesis or combination, decomposition, single replacement, double replacement, and combustion. I'm going to go into detail about each of these and what are the key things that you want to look out for, but you want to make sure that you can identify the types of chemical reactions. If it helps you, you can kind of write this picture or take a screenshot and put it in your notes. But again, we will have something that kind of gives you a better look into it. So this first one is the synthesis reaction. This one is also called the combination one. And the big reason why is because you're starting off with more than a couple of reactants, but you're only ending with one product. So for example, when I combine H2 and O2, I only produce water. Now a decomposition reaction is where there's only one reactant. This is where you're breaking it down. So you're starting with one thing, but it's breaking down into more than one. And an example of that is HgO produces Hg plus O2. To practice identifying them, what you kind of want to pay attention to is like what you're starting with. So for example, on number 1, I'm starting with AgCl. I don't see a plus sign. So when I'm just focusing on those first two, I know that this first one has to be, a decomposition because I'm starting with one reactant and I'm breaking it down. Why don't you guys try the next two? So looking at number 2, because I notice I have my one product with no plus sign, I know that this one has to be a synthesis or a combination. And on number 3, I'm going to pay attention again to that one product, and that tells me that I'm dealing with a synthesis because I'm not ending with more than one product. The next kind of reaction that you want to look at is a combustion reaction. The combustion reaction is where you're dealing with CO2 and H2O as my products, meaning that these are the things that I'm going to end up at the end, so on the right side of my arrow, and O2 is always going to be a reactant. You're always going to have what's called a hydrocarbon, which is just a carbon that is like a carbon and a hydrogen, sometimes with an oxygen that you have. So you're dealing with just your covalent compounds or your nonmetals. But anytime you're looking at a combustion, just look at those products. If you see CO2 and H2O and you see an O2 at that start, you know it's a combustion right away. One of the final ones that we have is a single replacement one. A single replacement reaction is called a date stealing reaction, and the big reason why is because you're going to have a single or lone element. Like in this example, I have like my C. What happens is that single or lone element is going to switch with the one in the compound and displace it. So you're always going to have a compound plus something that is all by itself. So it is the date stealing because, for example, you could say like, hey, I have my A on both sides, and that's in a compound, it's in a couple, and I have someone that is going to come in and steal that second position. To provide with an example, for example, I have like my zinc reacts with hydrochloric acid. Again, I'm going to see that individual metal. So I have zinc on the reactant side, and I have H2 on the product side, and then I have my compound. So in this case, I have the HCl, and then that zinc kicks out the H, takes place with the Cl. So as you can see, that Cl stays the same on both sides in the compound, but it's just the zinc takes out the H, and then the H switches out and is now by itself because the zinc displaced it. The last type of reaction that we're going to focus on is the double replacement, and this is the date switching reaction. In this one, you're going to have two types of compounds, and essentially what's going to happen is that the cations and anions are going to switch partners. So in this case, let's look at an example. So looking at a sample here, you want to kind of identify your cation. So in this case, my cation is Ag, and then I have my Na. My NO3, because it is a polyatomic, is going to stay together, and then I have my Cl. And again, what we're going to observe happen is that my Cl and my NO3 are going to switch places. So my AgNO3 now becomes an AgCl, and then my NaCl becomes an NaNO3. When you're doing this, you want to make sure that you crisscross correctly if you have to predict any products, but essentially we're going to see those metals just switch positions with the nonmetals, and now we have entirely new compounds. That completes this EdPuzzle. I know it was a little bit of a longer one. Make sure that you complete EdPuzzle number 3, that worksheet on Canvas. Um, Make sure that when you're doing it that you practice balancing equations and use your notes, and make sure that you submit these notes on Canvas for me to look at. If you have any questions, let me know, but have a good one.